To effectively explain transformer hookup rules, several resources and teaching strategies can be employed. For books and handouts, consider firstly Transformer Applications and Connections by Stanley E. Denenberg, published by McGraw-Hill Education. Secondly, explore the Industrial Power Systems Handbook by George W. Masters, available from CRC Press. Thirdly, Electrical Wiring Residential by Ray C. Mullin, published by Cengage Learning. And fourthly, the Transformer Handbook by W. T. Taylor, also from CRC Press, are valuable resources. Industry organizations offer additional materials. The NEA Power Distribution Learning Modules, accessible at www.nea.org/learning modules, include modules on transformer connections and grounding. The Electrical Training Alliance, or ETA, at www.electricaltrainingalliance.org provides handouts and presentations on transformer hookups. The International Brotherhood of Electrical Workers, or IBU, at www.ibu.org may offer materials or contacts for assistance. Online resources such as electrical transformer connections at www.electricafaru.com/transformer connections provide detailed explanations and diagrams. Transformer Connections: A Practical Guide, a white paper by Eaton Corporation, available at www.eaton.com/a/solutions/electrical/learning center/articles/white paper/transformer connections: A Practical Guide. HTML offers practical insights. Transformer hookups at www.electricalonline.com/transformer hookups. HTML covers different types of transformer hookups and their applications. When teaching Article 450.3 and related tables, begin with an overview of transformer grounding and primary protection importance. Break down the table into smaller sections, explaining each rule individually. Use real-life examples to illustrate rule applications and provide hands-on exercises for concept reinforcement. Diagrams or simulation software can demonstrate different connection configurations. Implement a progressive approach, starting with basic hookups and gradually advancing to complex scenarios. For Article 240, the NEC Handbook by Mark W. Early from the NFPA is a vital reference. The Electrical Inspection Manual with Checklists by Noel Williams from Cengage Learning and Electrical Code Essentials by Michael Holt from Delma Cengage Learning are also recommended. The specific code references include 450.3 and its tables, 240.4, 240.21c, 408.34, and 408.36. Article 450.3 specifically addresses transformer protection. The NEC requires transformers to have both primary and secondary overcurrent protection based on the transformer's voltage and current ratings. It details requirements for transformers over 600 volts and those under 600 volts. The primary side protection safeguards the transformer from overloads and short circuits originating in the primary circuit. Secondary side protection protects against faults on the secondary side and ensures that the transformer is not subjected to excessive current draw. The NEC tables associated with 450.3 provide specific percentages for sizing overcurrent devices, like circuit breakers or fuses, relative to the transformer's rated primary and secondary currents. These percentages vary based on the transformer's impedance and whether the overcurrent protection is on the primary or secondary side. Article 240 covers overcurrent protection in general. It outlines the requirements for protecting conductors and equipment from overcurrent conditions. 240.4 specifically addresses the protection of conductors. It states that conductors must be protected against overcurrent in accordance with their capacities, with some exceptions for specific applications like motor circuits or certain types of equipment. 240.21c provides specific rules for overcurrent protection of transformer secondary conductors. It allows for tap conductors from transformers to be protected at a location different from where the conductor receives its supply, provided certain conditions are met. These conditions typically involve limiting the length of the tap conductor and ensuring it is protected against physical damage. Articles 408.34 and 408.36 relate to panel board overcurrent protection. 408.34 requires that overcurrent protection be provided for lighting and appliance branch circuit panel boards. This ensures that the panel board and its branch circuits are protected from overloads and short circuits. 408.36 specifies the maximum number of overcurrent devices permitted in a lighting and appliance branch circuit panel board. The goal is to prevent overloading of the panel board's main bus and to ensure adequate protection for each branch circuit. Practical application in the field involves several steps. Firstly, determine the transformer specifications, including its kilovolt ampere, or kVAR, rating, primary voltage, and secondary voltage. This information is crucial for calculating the primary and secondary currents. Secondly, calculate the full load primary and secondary currents using the formulas. Primary current equals the kVA times 1000 divided by the primary voltage. Secondary current equals the kVA times 1000 divided by the secondary voltage. Thirdly, select the appropriate overcurrent protection devices, such as fuses or circuit breakers, based on the calculated currents and the percentages specified in NEC Table 450.3. Ensure that selected devices are rated to interrupt the available fault current at the installation location. Fourthly, for primary protection, the overcurrent device should be sized no larger than the percentage of the transformer's primary current specified in the NEC table. For secondary protection, the overcurrent device should be sized no larger than the percentage of the transformer's secondary current, also from the NEC table. Fifthly, when installing tap conductors from the transformer secondary, adhere to the requirements of 240.21c, ensuring that the tap conductor length is limited and properly protected. Sixthly, ensure that all panel boards connected to the transformer secondary are equipped with appropriate overcurrent protection, following the guidelines in 408.34 and 408.36. Verify that the number of overcurrent devices in the panel board does not exceed the maximum allowed. Common challenges often involve interpreting the NEC tables and applying the correct percentages for overcurrent protection. The NEC tables can be confusing due to the different percentages listed for various transformer impedance values and protection schemes. Additionally, installers sometimes struggle with calculating the available fault current, which is necessary to ensure that the overcurrent devices have adequate interrupting ratings. Overcoming these challenges requires a thorough understanding of transformer theory, NEC requirements, and practical field experience. It is important to consult with qualified engineers or electricians when in doubt and to stay updated on the latest code revisions and industry best practices. Real-world examples can help to illustrate these concepts. For example, consider a 75 kVA transformer with a primary voltage of 480 volts and a secondary voltage of 208/120 volts. The primary current calculation involves dividing 75 kVA by 480 volts, resulting in approximately 90.2 amps. If the NEC table allows for 125% overcurrent protection on the primary side, the maximum size of the primary overcurrent device would be 1.25 times 90.2 amps, which equals about 112.75 amps. Therefore, a 110 amps or 125 amps circuit breaker or fuse would be appropriate, depending on the standard sizes available and the specific requirements of the installation. The secondary current calculation involves dividing 75 kVA by 208 volts, resulting in approximately 208.2 amps. If the NEC table allows for 125% overcurrent protection on the secondary side, the maximum size of the secondary overcurrent device would be 1.25 times 208.2 amps, which equals about 260.25 amps. Therefore, a 250 amps or 300 amp circuit breaker or fuse would be appropriate, depending on the standard sizes available and the specific requirements of the installation. These examples demonstrate the practical application of NEC rules and the importance of accurate calculations for ensuring proper transformer protection. Regularly updating materials and references ensures alignment with the latest NEC requirements. Always consult the most recent edition of the NEC and any applicable local codes or regulations to ensure compliance with current standards.